Okay, in this lecture, we're going to start in a new chapter. This is chapter 4, and it's on applications of differentiation. So we're going to start in 4.1, and we're going to look at minimum or maximum and minimum values. So it turns out that the derivative, so if we have a nice enough function that is, and usually nice enough means either continuous or differentiable, it turns out that the derivative can tell you, give you some information about where a function attains or has a minimum or a maximum. And again, you can imagine that this has, an endless number of applications, not just within mathematics. Lots of ideas in mathematics have applications in mathematics, but then there's applications outside of mathematics. So trying to describe, the revenue and you want maximum profits or whatever. So, such functions are usually approximated as continuous or maybe even differentiable. And you can use the tools of calculus to tell you when, you have a maximum revenue, say, or maximum profit, or whatever. That's just a really simple, uh, maybe even uninteresting example, but you can imagine all sorts of examples. All right, so let me share my screen. All right, so hopefully you can see what I can see. So it's gonna turn out that there are two types of minimums or maximums, or two types of extrema. So let me just say, um, let's say we have extrema that. So this is, sorry, first of all, this is 4.1. This is maximum and minimum values. So extrema, the term extrema can refer to, is just a generic term referring to either a minimum, let's say a minimum or maximum value of a function. And these come in two types or two flavors. So we have two types or slash flavors. Oops. You can have absolute, so you could have absolute extrema. So either absolute maximum or absolute minimum, because extrema is just a generic term to refer to a minimum or a maximum. Or you could have relative. I think the better term is local. I don't know what the book uses. Let me see what does the book. Actually, the book uses local, so I'm not going to use relative at all. Some books use relative. I prefer local. So, or you could have a local extrema, and I think the term local is like more. It's a more accurate term to of what it's describing. So as you might guess, the term local. So you could have a local extrema, and that could be either a local minimum or a local maximum, and that should indicate to you that this maximum or minimum value is a maximum or minimum. This local maximum or minimum is is a maximum or minimum for near values near a given value. Let me pull the book open because it has a few definitions. So here's the definition of absolute, the absolute extrema version. So this first definition is about absolute, oops, absolute extrema. So you have a number c in the domain of the function f, and then f of c. So you have an extrema at c, and then f of c is the extreme value, which could be either a minimum or maximum. And you call it a absolute maximum of the function f if f of c is bigger than all of the outputs. So f of c is bigger than f of x for every x in the domain. So it's like remember your function, your f value is the output of the function. So it's saying that this particular output, f of c, is bigger than every other output. And then absolute minimum, as you can guess, pretty straightforward. It's just like the dual or the analog, and it's just you just switch the inequality right here. So now it's less than. So this output f of c is less than every other output f of x, and that's for everything in the domain. So your domain could be very large, it could be even the whole real line, and you're saying it's bigger than every value. And such values do exist. It's kind of rare, I would say, at least in my experience, that you have an absolute max or minimum. Um, so this is a useful notion. Sometimes it's useful to always also know have a local version of this to talk about local extrema, local minimum or maximum. So this is going to be the local version. So this is a local extrema. And now I'm looking at this and I'm realizing I don't like how it's saying, how it's phrasing this. I mean, it's pretty being kind of vague. So you have a number f of c, where c is in the domain of f. So let's say f is a function from d to some set e, and then c is in the domain, and then f of c, which is in e, so the output set, the codomain, is a local maximum if f of c is bigger than f of x, not for all x in the domain, but just all the x near c. And how you phrase that is that there exists a small interval containing c, and you're looking at those x values in that c. So, and then um, a local minimum if the opposite inequality holds. And again, it's not for all x in this domain, but just x near it. So let me actually rephrase this slightly, just so you can sort of connect this definition to maybe some other ideas. So there's actually an epsilon reformulation of local minimum. So here's a definition, or I should say local extrema. So definition of local extrema. So we'll say let's be a little more precise. F a function from a set D to E. And again, just take D and E to be some set of real numbers. And then we're going to say, and C is in the domain of the function, then F of C is a local minimum, or let's say local maximum. So here's sort of an alternate way of expressing this. That's a local maximum of f if f of c is greater than f of x. Oh, sorry, I don't want to just say that. Because I'm basically saying the exact same thing that the book says. It's a little different what I want to say. So it's a local maximum of f if there exists, well, let's say delta actually, because in the limit definition we talked about for every epsilon there's a delta. There exists a delta. So we're going to say there exists a delta such that if x is really close to c, it's within delta units, then f of c is bigger than f of x. So in other words, if you're pretty close with this inequality, absolute value inequality says is that if you can find a delta, and then you look at any x that's really close to c, it's within delta units of c, then the output of the function better be bigger than this f of c better be bigger than all of these f of x's, where your x satisfies this inequality. These are x's are, you could say, let's say these x's are the things that are near, quote unquote, near c. So that's what that phrase near means. It means that you can find a delta probably very small, such that x minus the distance from x to c is very small. It's within delta units. And then your function will just always be the value of the function at c will always be bigger than all of those values near c. And then the local minimum is basically the same thing. So, or yeah, local minimum. So f of c is a local minimum of f if, oops, that's not good. If there exists, oops, if there exists delta bigger than 0, some small distance, such that if x minus c is less than delta, the active value, then f of c is less than or equal to f of x. So this is equivalent to the definition stated in the book. Maybe it's pretty obvious, maybe it's not. So take some time to ponder why those are basically the same thing, same definitions. And also, I'm also trying to describe what does it mean to be near. This is a really important math concept in mathematics. Being near, um, and you can alternatively say this. If x satisfies this inequality, then that means x is in the following open set. It's going to be c minus delta, c plus delta. So in other words, you satisfy this inequality here if and only if x is in that set, which is even better because notice I'm not making, when I talk about this open set, I'm not making reference to some notion of distance. Absolute value is a notion of distance. And when you get further in mathematics, you'll see that it's not always possible. You'll have spaces where it's not always possible to talk about distance in like this sense, in the sense that we talk about it. But you can talk about open sets. So this is a really important concept. It's a concept of being near. In fact, there's a whole branch of mathematics that I've mentioned before, I think, called topology, which kind of tries to make sense of this notion of points being near each other. What does it mean to be near? So topology makes this idea it makes this idea more precise, and you don't actually need a notion of distance on your space. Lots of spaces will have a distance, a notion of distance, a way of measuring distance between points. So it's perfectly fine to imagine all of your spaces having some sort of distance function, a way of measuring distance, but there are some spaces where you don't have such a distance. So it's important to be able to generalize this idea of being near. All right, so that's all I want to say for that. So let me pull up the book again so we can look at some pictures. So here we go. So we have, I guess, what does figure 1 say? All right, so it looks like for figure 1, the function is defined from 1 to 7. So we have this function, we're graphing some function from 1 to 7 to the real numbers. And I guess you could say the image would be 2 to, I guess, 5, maybe, looks like, but that doesn't matter. But you can see that, like, geometrically, like intuitively, I guess, or geometrically, like this point right here should correspond to a maximum, this point should correspond to a minimum. So this point right here would be f of 3, and I guess it equals 5. This point right here would correspond to f of 6, and it equals 2. And so you can kind of see, yeah, sure, it does satisfy. So this value right here satisfies the definition of absolute max. It's bigger than every other output on the whole domain, and our whole domain is 1 to 7. And then this right here, this other point right here, which does satisfy the definition of absolute minimum. It's going to be less than, if you just take not just points near it, so like a point here, it's definitely smaller than that. It has the height of it is definitely less than the height of this point right here. But you can just take any point in the domain and just trace up its value on the curve, and you can see that this point right here is definitely smaller than all of those other ones. So that's absolute max. But what about absolute? What about local? Or sorry, that's absolute extrema. What about local extrema? Well, in this case, I think we're gonna imagine is that this function just keeps going off to infinity like this, off to infinity like this. So there's really no absolute maximum in this case. There's no, well, you could say, or you could phrase it as a global maximum. It's a maximum over the whole domain. So this example here, we'll say no absolute extrema, but it does have local extrema. So for example, we have a local minimum here, a local max, a local min. Now, why are these local maxes and mins? Do they satisfy this definition here? Well, the idea is, yeah, look, if you take it's actually showing you what how close you had to be to the point. So there's this interval right here, I, J, and K. It's showing you the deltas you need in these cases, this case. So remember for the definition I wrote, you if you're a local max or a local min, if you can find a delta such that when you look at the open interval centered at that point of length delta, your function will either be bigger than every value or smaller than every value. And so you can see, like, yeah, if I just take a small interval, like say this interval, from here to here, centered at 4. Yeah, look, this point at 4, so f of 4, I guess we're calling this function f. We'll say this is the graph f. F of 4, this value right here, definitely is smaller than every value, other value on the interval, on this interval from here to here. Now, it's definitely not the um it's not gonna be the absolute minimum though, because look at there's this point over here that's even smaller than this. But note this point right here is not included in this interval right here. So we're okay. Because local means near. We're near a point. It's gonna be a local minimum on like restricted to this small subset of the domain. Um, and if actually in this case, now that I'm thinking about it, we do have based on like what the behavior of the graph is, it goes off like this and it goes off like this. This point right here will actually be, and it says it here. I didn't realize that I wasn't reading that. It is this point right here is both a local and an absolute minimum. So it's possible you can have both. You can have, or you could have one but not the other. Um, so let's see. So that's why that's why this is a local minimum. This point right here is a local max, and so you can see that by taking this interval right here centered at 8. So this will be some delta. So this would be like 8 plus delta. I don't know exactly what. Maybe you could work it out. 8 minus delta. So this is the interval centered at 8 with the endpoints, kind of looks like a delta. It's 8 minus delta right there, and 8 plus delta. So just a small interval centered at 8. And then you can see that the value of the function is at 8 here is bigger than every other value on the interval. And notice you could actually take the interval bigger. You could maybe even take it here or here. You could expand the interval and then look at the value and you'd be fine. I guess you could take it all the way, say like if you trace it over, it like kind of ends here. You could take the interval to be from here to way out here, maybe even interval centered at 8, and it will be bigger than every value. But sometimes you don't care about the interval being big. You just want to look at points near a given point, near the point of interest. But now, let's say you can see though, however, again, based on the trend of this graph, that although this is a local maximum, it's not going to be an absolute or global maximum because the function at some point, you can see, let me erase this a little bit. You can see, like if you trace this over, there are definitely points in the domain. So maybe like even 0, say like if you trace it, it's going to intersect at 0. So you here and then you trace it all the way up. And at this point, it's at a higher value than that. So It's going to be a local max, but not being a global max. And so this statement right here I made down here is not true. There are absolute extrema. There we have an absolute minimum right here. So hopefully this distinction between absolute and local is clear, and hopefully the definition of a local or local extrema is clear. All right, so let's see. All right, so let's look at this graph some more. And so we can see, I think this graph right here really contains basically everything we need to know. Or maybe I'm thinking too far ahead, actually. Let's see, what is this example right here? I think it's kind of boring. So they just graph it, and there's the graph. So here's f of x on this interval, you graph it over here. Okay, here's the absolute max. This value is higher than this one. This will be a minimum, absolute and local minimum. This will be a local. All right, maybe I should start late. Let's see. All right, anyways, I'm not going to write it all down, but I'm just going to say it out loud. So let me start over. All right, so this point right here is going to be higher than this point. So this is going to be this is a local absolute maximum. It's not a it's not a absolute, it's not a local max though, because this point, like if you trace it down here, like, well, I guess it's at one. Let's say it's at -1. You can't define the any open interval containing -1 is going to be outside the range or the domain, right? Because the domain stops at -1. I should have also mentioned that. Let me pull this definition, this local version with these epsilons, deltas. Not only do you need to satisfy, and it's kind of obvious, not only do you need to be satisfy this inequality, but x also has to be in the domain. So you have to be in the domain of the function and be very close. That's what this inequality expresses. Otherwise, you can't take f of x. It wouldn't make sense to evaluate the function f of f if you're not in the domain. So satisfying this inequality isn't enough. It might not make sense to evaluate the function at that point. You have to satisfy this inequality here and be in the domain as well. So that's why for this example right here, this graph, this is not going to be a local maximum because there's nothing over to the left of -1. That those points are not in the domain. So it doesn't make sense to talk about an interval centered at -1 and in the domain because there is no such interval. So for this one we have a local minimum because I mean you can take the interval, I guess, from -1 to 1, so that's going to be centered at 0. So 0 is the point at this point right here is going to be a local minimum but not an absolute minimum. This one here is going to be a local maximum. Again, you could take, I guess, the interval from 0 to 2, so that'd be centered at 1. And it's going to be a local maximum. It's going to be a maximum on that interval, but it's not a global or absolute max. And then right here we have this will be a local minimum, and it'll be a absolute minimum. And you can take basically any interval. You could take the whole interval basically from -1 to 4. That will work. And then this will be nothing. All right, let's see. So here is a very intuitive. I'm gonna just kind of, yeah, I'll let you read through these examples if you want. So, oh, I guess I'll just, yeah, this is a good distinction here. It's possible to have no extrema at all. So for x squared, we do have an extrema at 0. this point right here will be a local and an absolute minimum. And it's pretty clear from the graph, but you can see check from by definition. So yeah, you can see that um if the function is given by x squared, then this interval inequality is clearly satisfied for every real number. Because if you take any number and you square it, it's definitely going to be bigger than or equal to zero. And that's the reason why it's absolute and a local minimum is because this inequality is true for all x. Now, for this point right here, you can have at zero, it's going to be neither a minimum or a maximum, neither absolute or local. And that's because if you take any interval centered at zero, just take that one, and you look at like the f value. Let's actually take it a little bit bigger so it's clear what's going on. All right, hopefully this responds soon enough. All right, this is irritating. Why that's doing that? This is ridiculous. Okay. Feel free to skip this part if you want. Let me stop sharing for a moment. Figure out what's wrong with this. Of course, as soon as I stop sharing it, it works. All right, so let's erase this right here. And let's figure out why this is neither local nor absolute minimum or maximum. There's no extreme at this point. Why is that the case? Well, if you just take any interval, we'll take it big enough so it's clear what's going on. And you take a point over here and look at the f of x value, it's going to be smaller than this. But then if you take a point here and look at the f of x value, it's going to be bigger than that. And no, and remember what the definition of absolute, or let's say local minimum or maximum. In order to be a local minimum or maximum, you have to be either larger than the given value on the whole interval, or you have to be smaller than the given value. So this point right here on the entire interval. But if you take any interval centered at zero, you can find a point which is bigger and smaller. You can find, or sorry, not a single point. You can find a point where it's smaller than the value or it's bigger than the value. So you can just take a point left of zero and it'll be smaller. You can take a point to the right of zero and it'll be bigger. So this holds true for any interval. So in other words, remember what the definition of local extrema is. It's that there exists a delta. This shows you that for any delta, meaning for any interval centered at zero, you can find a point that's bigger and a point that's smaller than that point zero. So it's not going to matter. So it won't be either one. All right. So now let's look at this so-called extreme value theorem. This is going to be a really important theorem, actually, and have a lot of theoretical use. It's going to help us prove other theorems. And intuitively, it should be clear that this is true. I'm going to pull up a proof. There's this proof I found here. It's not that hard to follow. I think it's kind of a neat proof. But what does the extreme value theorem say? So it says if you have a continuous function, so you have a nice function on a closed interval, then the function attains a maximum value and a minimum value. So it attains a absolute maximum f of c and an absolute minimum f of d for some numbers c and d in your domain, which is this closed interval. So and this is going to be this is going to generalize a lot, actually. It turns out all you need is the fact that this interval right here is a compact space. So if you have a continuous function from like a compact space K, the real numbers, then this same result holds. So, and this is as a result that comes from topology. So this is a compact space, and there are lots of them. All right, so intuitively this is hopefully clear. So if you let's look at some possibilities. And of course the numbers C and D could just be the endpoints of this interval. You could have the minimum and the maximum occur at the endpoints. So the idea is like, all right, let's imagine you're tracing a continuous function, and that's important. It's a continuous function. So we definitely know that there's the endpoints. Let me just draw it over here actually, because these pictures are already drawn. I want to imagine, let's try drawing this picture and show that the conclusion is forced on us. So we have like A and D, or A and B, I should say. Now, these numbers are kind of fixed, so we know f of A is, say, here. And then there's actually a couple possibilities for f of b. It could be at the same height. And then what could happen is that we could be a constant function. And if you're a constant function, you definitely obtain a minimum and maximum. In fact, every value is a minimum and a maximum because there's just no variation. That's one possibility. Another possibility is that you're not constant, but these are at the same height, right? So if you're not constant, that means there's a point, there are 2 points where you're bigger and smaller. So maybe you're here and then you're here. But if that happens, now this is a continuous function. So it has to connect here, and then it would have to like kind of connect like this, and then maybe go up like this. But you see that you're the only way you can draw this continuous function is by connecting them, and you can see that there you already get your minimum and your maximum. So there's like no way of avoiding it. There's like you can't jump around in some odd, unusual way. So these are just a couple examples illustrating that if you try to what this says, this extreme value theorem says it's impossible to draw a continuous function where you don't have a minimum and a maximum. And you can just playing around with examples. If you try to draw a continuous function where this doesn't happen, it's not gonna. It is impossible to draw because you can't. So what does the proof look like? So the proof is not that bad actually. The book says, "Ooh, this proof is." Of course the extreme value theorem is very intuitive. Intuitive, very possible, but the proof is difficult, and it's actually not that bad. Hey? The proof is not bad to go through. So I want to go through it really quickly. So I'll read this with you. So here's how the proof goes. So we're just going to look at when at the case where you have when f attains a maximum value, because proving that f has a minimum value is like the exact same argument. There's like basically no difference. And you can maybe even see how you argue that from this proof. So we're just going to prove that f has a maximum. So what are the assumptions? F is continuous on this interval, which is essentially every example we're going to look at. So this theorem applies to every example we're going to look at. All right, so here's how it goes. So if you're continuous on this interval, there is one thing that I didn't prove, and this is actually the hard part. I think maybe this is what the book was saying, that's the hard part. But this is going to be clear. Watch. If f is continuous on this interval, then it has to be bounded on the interval. And that's kind of clear. So let me show you what I mean by bounded by trying to draw something. So like, what would it mean to be? So we have, sorry, let's say we have this function from A to B and it's continuous. Again, let's try to draw a continuous function on this closed interval that's unbounded. Is that possible? And I'm going to tell you that it's not possible. So maybe you start here, and then to be unbounded, you would have to go off to infinity at some point, right? So to be unbounded, you'd have to keep growing and growing and growing and growing and growing. But you can't just and let's say like f of c of b is like here. None of these values are infinite, right? The function evaluated at any of the points is not infinite. But notice, like, you can't just keep going off like this and then keep going up here and then jump down here. That would be discontinuous. At some point, you have to start coming back down like this. And then you clearly, this would be, of course, this would be your maximum, But the point is that this is a bound. This is an upper bound. Of course, you have this lower bound down here at this point right here. Um, so being bounded is a little bit different than having a minimum or maximum because all this shows is that there's this value that's smaller than every value, and then there's this value up here that's bigger than every value. But there's no reason to think that your curve actually goes through it. Maybe it gets really close to it, but it never actually goes through it. So that's all that this boundedness theorem says, is that you get really close to some line, vertical line, but maybe you don't actually touch it. But notice you can see that this vertical line that you get close to has to, or sorry, horizontal line that you go through has to exist, because if you just kept going up here, up off to infinity forever, but then you have this value down here, there's no way to connect it to the graph if you're going off to infinity. You have to stop going upward at some point, you go down. So in other words, what this shows is that it's impossible. If you have a continuous function, you have to be bounded. You can't go off to infinity. All right, so how does that help us? Well, so if it's going to be bounded, so you have this function, it's continuous on this interval, then you know it has to be bounded on the interval. And so you can say, call your upper bound M, and you can say it's actually a least upper bound. It's the smallest upper bound. There are going to be lots of upper bounds for your function, but there's going to be a smallest one. And what we want to do is to show that there exists some C such that f of C equals this upper bound. And once you do that, you're done. As I say, there's once you can show that, there's nothing more to do. You've just shown that f attains its maximum on an interval. So that's what we want to do. We want to show that there exists an f of C such that f of C, sorry, we want to show that there exists a C in this interval such that f of C equals M. So here's how the proof goes. Assume that it doesn't happen. Assume by contradiction. Suppose there is no C in the interval A to B. Well, if there's no C such that f of C equals M, but f of C is less than or equal to M, then we know that f of x, in this case, has to be strictly less than M, because it can't equal it, right? We're assuming the opposite, but it definitely has to be smaller than it because M is an upper bound. In fact, it's going to be the least upper bound, which is going to be important. So here's how we do this. We're going to define a new function g as follows. It's going to be 1 over M, or least upper bound, minus f of x. And this is good because actually, because f of x is less than m, m minus f of x will be positive, so g of x will be positive because you're taking 1 over a positive number. Right here, this is going to be 1 over a positive number. G of x is 1 over a positive number for every x. And in fact, it's going to be continuous. This is going to be a continuous function. So because g of x is a continuous function and it's defined on this whole interval, it's also got to be bounded, right? By this boundedness theorem, which I did not state, but it's pretty clear that it has to be bounded. The boundedness theorem is pretty clearly true. The function can't go off to infinity. It's impossible. You'll destroy continuity of your function, basically. So we define this new function g of x. It also has to be, it is also continuous, so it also has to be bounded. So what that means is that there exists some positive number, right? Because g of x is positive, so whatever its bound is, it also has to be positive. Because the graph is, so if you graph g of x, it's going to be above the x-axis. So its upper bound also has to be above the x-axis. So there exists some positive number k such that g of x is less than or equal to k, and that's for every x within the interval. So what that means, what does this inequality mean right here? G of x is less than or equal to k. Well, remember how g of x is defined. So if you just plug in the definition for g of x, that you get this inequality. Now, if you rearrange this inequality, you're going to get f of x is less than, you do some manipulation, do some algebra. As I say here, I think they tell you, upon multiplication of both sides by this positive number, m minus f of x, followed by division on both sides by k, what you'll get for every x is that f of x is less than or equal to m minus 1 over k. This is a typo. This should be capital K, but who cares? But why is this impossible? Why is this the contradiction? This is a typical method of proof in mathematics, you do a proof by contradiction. You assume the opposite and you get this absurd statement. Why is this statement right here absurd? Well, remember, so if you take m minus 1 over k, you've shrunk the number m, right? You've just subtracted a little bit off for m. So this number, m minus 1 over k, is less than, strictly less than m, right? But so this shows that f of x has this upper bound right here, m minus 1 over k, and this upper bound right here, m minus 1 over k, is strictly less than m. But remember, we assumed that m was the least upper bound, which is a contradiction because we just constructed this other number, which is an upper bound, and it's less than m. So this is the contradiction. This is impossible because it contradicts the assumption that m was an upper bound. So what that means is that what we initially assumed can't be true. And what we initially assumed is that there was no c such that f of c equals m. So that assumption is false. So that means there does exist a c such that f of c is equal to f of m. Sorry, such that f of c equals m. So as it says, this leaves us as the only possibility that there's some c in the interval where f of c equals m. And that is to say, f attains its maximum. So that's the proof of the extreme value theorem. You do need this boundedness theorem, but hopefully that's pretty clearly true also. So that's how that proof works out. So you could search this if you want to read this for yourself. I just found it. I just searched proof of the extreme value theorem, and this is the first thing I came up and I saw it, and I thought it was a pretty decent proof actually. And if you're curious, you can go search for a proof of the boundedness theorem. That might not be as easy. I'm not sure. Because again, it's intuitively clear, intuitively true. But if you want to work through any of these proofs one-on-one, feel free to email me and we can set something up. All right, so this is an interesting theorem that has lots of consequences. But let's look at some, and we'll see some consequences of the extreme value theorem later. But now let's notice something about these. Oh, here's an example illustrating how you can not have the extreme value theorem hold. It could fail. So it says theorem 5, 9, and 10 show a function that need not possess extreme values if either hypothesis that you are continuous or your function is defined in a closed interval is omitted. So here we have a discontinuity at this point. So when you have that, you can see that there is going to be no maximum, right? You might think, oh, well, this point right here is a maximum, but it's not because it's excluded. There's a circle. So like you could say, well, what about this point? Isn't that a maximum? No, because you can get closer up. You can get arbitrarily close to this point you've removed. So there'll always be a bigger and bigger value. So this will not have a maximum. This one it does have a minimum at this point, but remember the extreme value theorem says you'll have both a minimum and a maximum. So if you have a discontinuity like this, you're gonna lose one or possibly both. You're not gonna have both if you'd assume that your function is not continuous like this. So you could say like, well, what about this? Is this a maximum? No, because there's this value up here that's bigger. Okay, is that the maximum? No, because there's this value that's here that's bigger. What about that? And you could just get arbitrarily close to this point you're moving. So no, there is no maximum, and we're assuming not continuity. What about this one? Well, in this case, you're assuming continuity, but now your interval is not closed. You're looking at the interval from 0 to 2, and this is not a closed, or to use more rigorous, or not rigorous, but more telling language, is that it's not compact. That's what it's going to turn out to be. It's not a compact interval. So you need closed and continuity. So in this case, you have neither a minimum. So you have no maximum or minimum. Because again, you could say, like, is this the minimum point? No, because you can get smaller. Well, is that the minimum point? No, because you can get smaller. And you can get arbitrarily close to this point you've removed. And the same type of argument over here. Is this a maximum? No, because you can get bigger. Was this point a maximum? No, because you can just keep traveling up and getting arbitrarily close to 2. All right, so let's look at actually let me pause for a moment and resume in a second. Okay, sorry about the interruption. So let me share my screen. So we now have hopefully a clear idea of what an absolute extrema and local extrema are. And we saw a proof of the extreme value theorem, and we also saw that intuitively it should be true, but then we also have this proof to show that it is in fact true. So think about those intuitive reasons why this is true. Think about maybe even the proof and read through that if you're interested. Now let's look at a particular types of functions, these differentiable functions, and ask whether or not the derivative can tell us anything about whether a function has local extrema, a local minimum or maximum. So you notice and basically all these examples, we have not only are these functions continuous, so like this example, these ones are here. This example, uh, oops, this example, even the cosine right here, this example, and all these examples, well, actually this one not here. All of these functions are smooth, they're differentiable, right? With the exception of this one right here. So all these are very nice functions. And what can you, if you look at the graph where we do have a local minimum or maximum, what do you notice about that? Take a second to think about it. What can you say about the derivative of this function at these points? So if you said that the derivative is 0, you would be right. Notice what is the tangent line? Let's draw some tangent lines at these points. If you look at them, these are horizontal lines, right? So this is going to give us, this observation is going to give us a connection between local extrema of a differentiable function, that is a nice enough function, and the derivative. So there's a connection between local extrema and the derivative. Again, you have, these are horizontal tangent lines, all at these points. So these are points where the derivative is 0. That's what, remember, the derivative tells us the slope of the tangent line at a given point. So it turns out that this is true. We have this necessary condition. So this is a necessary condition for local extrema. What it says, it basically says, so if I give you a random function, say it's differentiable, it might not be at all obvious where you have local minimum or maximums. What this tells you though is it gives you this Fermat's theorem right here. It gives you a way of narrowing the search space to try to find the local extrema. What this says is that if you have a local minimum or maximum, wherever it is, the derivative better be 0 there. It does not say, however, that if the derivative is 0 there, then it must be a local minimum or maximum. All it says is that if you have a local minimum or maximum, your derivative better be 0 at those points. So this, what you would say is that this gives us a necessary, oops, didn't finish the whole statement. It's a necessary condition for having local extrema, we'll say. That is, if you have a local minimum or maximum, if you have a local extrema at C, then necessarily f prime of C is 0. And you can see that from this graph as well. Now, why is this? Well, let's look at a proof and then we'll figure out why the converse statement does not hold. Why isn't it also sufficient to have 0 derivative and then conclude that you have a local minimum or maximum at that? Then there's easy examples to see why this is not the case. So here's a proof. It's not that bad. I guess we'll go through it very quick. So we're gonna suppose that we just, without loss of generality, let's say f has a local max. And the other case is gonna work very similarly. So by according to the definition 2 for local max, that means you have f of c is bigger than f of x for all x sufficiently close to c, that is on some small interval around centered at c. So what this means is that if you take h to be sufficiently close to zero, that is sufficiently small. So if you take h prime to be sorry, not h prime. If you take absolute value of h to be small, that's what it means to be close to zero. Then f of c, f of h plus c is a point near c because h is very small. So now you can rearrange this inequality like so to get this, and then now we'll just take h to be a positive number for now, and we're going to divide this inequality right here by h, and we're not going to switch the inequality. It's going to stay like that. Eventually, we're going to look at h being negative, and it will reverse the inequality, but that's okay. So now, when we take the limit of this, well, now first of all, we know what is this? This is our derivative right here. This is the difference quotient. So we're seeing the derivative pop up naturally. So you take the limit as as h goes to 0 from the right. So you're going to take the limit of this inequality. So if you know that this thing is less than, if this difference quotient is less than 0, then the limits better be then the limits better satisfy this inequality as well. So when you take the limit of 0, it's obviously going to be 0. But then, as they know, f prime of c exists. So f prime of c, which is this difference quotient as h just goes to 0, is the same thing as taking the difference quotient, but h goes to 0 from the right. Because remember, if the limit exists, then the left hand and the right hand limits exist, and they have to be equal to each other. So what this shows, we just showed that this limit right here is less than 0. So that shows that f prime of c is less than 0. Now what we're going to do, so that's when we take h to be a positive number up here. So now we're going to take h to be a negative number, and you divide this inequality right here with this difference quotient by h. Oh, sorry, you divide this inequality right here. Now divide this inequality right here by h, and it's going to reverse this sign right here. So we get this right here. And now we're going to just play the same game. We're going to take the limit, we're going to take a left-hand limit as h, so we're going to take the limit as h goes to 0 from the left. And if you take the limit of this inequality, I should say, then the limits better satisfy the inequality as well. So the limit of this difference quotient is going to be bigger than or equal to 0. But we're assuming that the function is differentiable. So this exists and it equals this. The limit as h goes to 0, which has to equal also this left-handed limit. So this shows that f of prime of c is bigger than or equal to 0. But don't forget that we showed that it's also less than or equal to 0, right? So what we've shown all together, putting everything together, is that f prime of c is bigger than or equal to 0 and is less than or equal to 0. So if you combine these, the only possibility is that f prime of c just equals 0. And that's the conclusion. That's what Fermat's theorem says. So Fermat's theorem says that if you have a local minimum or maximum at a point C, so local minimum or maximum, a local extrema at C, then necessarily your derivative has to be 0 at that point. You have to have a horizontal tangent line, and this is the proof right here. So not terrible. Maybe not completely straightforward, but that's unfortunately how a lot of proofs in mathematics works. They're not like the intuition for why a result is true is immediate. It's like, yeah, just start drawing tangent lines. You can see that they're horizontal. Pretty clear. But not the proof doesn't always so the statement is sometimes obvious, but the proof of the statement is not always obvious. And that's what makes mathematics maybe in some aspects difficult and or interesting because it's like figuring out how to prove this obvious statement. It's like it also makes the mathematics annoying, honestly, because it's like all these statements are so obvious, and it's like, yeah, this is obviously true, but the proof's like so damn not straightforward, and it can be annoying. So that's unfortunate fact in mathematics. So here's a natural question that can arise. If f prime of c is zero, does f have a local extrema at x equals c? That is, does it have a local minimum or maximum? And the answer is unfortunately no. It's not all. This is so. In other words, we're asking, does converse hold? This is what's called the converse statement. Does the converse statement hold? And the answer is no, no. And it's pretty easy to come up with a counterexample. So unfortunately, no. These things are not the same. In other words, and so to see this, just take f to be this function from r to r, and we'll take our trusty old cube function. So if you take the derivative, you get 3x squared, and if you plug in f of 0, f prime of 0, you get 3 times 0 squared, which is 0. So the derivative is 0 at 0, but remember, 0 is not extrema. So remember, we looked at that example way up here. This point right here at 0 was not, this right here is not a minimum nor maximum. So it's the derivative of the function is 0 at 0, but 0 itself is not a minimum or a maximum. So that shows that this question doesn't always have a positive answer. So it's not always true that if your derivative is 0 at a given point, then you have a local extrema at that point. So make sure you keep this distinction in your head. So in other words, we have a statement like P implies Q, right? That's our Fermat's theorem, but Q does not imply P. So you got to keep these statements, you got to keep the implications straight in your head. And yeah, so this is the example they look at. So you have this function f x cubed. Here's the derivative, f prime of 0 is 0, but f has neither minimum nor maximum at 0. All right, so let's see, what is the next thing? Um, so we have this example here, the function. So this function f of x is equal to absolute value of x is not differentiable at this point. We saw that when we compute, we computed left hand, right hand limits, the derivative, and showed that on the one hand, if you approach 0 from the right, you get the difference quotient is 1. But if you approach 0 from the left, the limit of the difference quotient is -1. And you can see that because like this branch right here has slope 1. This branch right here has slope -1. So this point 0 is not going to be a point that where you're differentiable. Um, and that's also because it's a kink. You have this kink or this corner in the graph. But this is a local minimum. It's a local extrema. So the function, the Fermat's theorem doesn't really apply to these kinds of functions. But so in other words, so Fermat's theorem only applies to differentiable functions, but it's possible for a function that's not differentiable, like the absolute value function, to have a minimum or maximum. So you can still have that. So you have to be careful. You have to be careful when you're dealing with functions which are not differentiable, like the absolute value function. You can still have a minimum or a maximum. So let's see. So here's this warning. Example 5 and 6 show that we must be careful when applying Fermat's theorem. Example 5 demonstrates that even if your derivative is 0 at C, you can not have neither a minimum or maximum. So that's this example right here. So that what that says is that as I was saying, the converse of Fermat's theorem is false in general. And on the other hand, there may be an extreme value even though the derivative doesn't exist at the point, as in the case of example 6, which is this right here, this absolute value function. So what does Fermat's theorem tell us? Well, it tells us that if we want to find minimums or maximums of a differentiable function, we should at least start looking at the extreme values of f where there's derivative 0, or at least where this point doesn't exist. Because you could have, like in the case of the absolute value, you could have this point right here, where you don't exist, but you still have a minimum. So to find extrema, local or minimum, this tells you that you should at least start looking at those points where you have zero derivative or its derivative does not exist. It's not guaranteed to have a minimum or a maximum there, but that's where they could be. So that's all that Fermat's theorem says. It's not a condition telling you where you're going to have minimum or maximums. It's a condition saying where you could have minimum or maximums. That's an important distinction. So we're going to give these types of values C a special name. So we're going to say a critical number of a function f is a number C in the domain of the function f such that either the derivative is 0 or the derivative does not exist at that point. And this is where you could have a minimum or maximum, not guaranteed. And then we can rephrase, Fermat's theorem can be rephrased as follows. It can be said as stated as follows. If f has a local minimum or maximum, so it has local extrema at C, then C is a critical point. That is, it's a point where the derivative is 0 or it doesn't exist. So this theorem allows us to narrow the search space in finding extrema. All right, so here, let's see, what do we have a couple examples. All right, so let's work through these examples. I'll open up Paint again. So let's go through maybe 7 and 8, and then that will be it, I think. So we have example 7. So we have, let's see, actually, so I'm just going to do part B. So we want to find critical numbers of f of x is equal to x to the 3/5 times 4 minus x. So we could do product rule. So first of all, we have to find the derivative, right? We need to know where's the derivative 0 or where does it not exist. So we could do product rule here, but it's actually unnecessary. So we can just distribute this x to the 3/5 through, and then we get so 4x to the 3/5, and then x to the, I guess, 8/5. And then that will imply that the derivative is equal to, so it's gonna be 4 times 3/5 x to the negative 2/5 minus 8/5 times x to the 3/5, I guess. Let me subtract 1. So now we want to simplify a little bit and then probably factor. So we're going to get 12 over 5 x to the negative 2/5 minus 8/5 x to the 3/5. And then what we want to do is we want to factor out x to the negative 2/5, I think. So if you factor out x to the negative 2/5, inside you'll get 12 over 5, and then minus, let's see, it's going to be 8 over 5. Actually, you know what? I'm going to factor out. I can factor out a little bit more. So I'm going to factor out, let's say, 2/5. So it's going to be 2/5, and then times x to the negative 2/5. And then in the parentheses, I will have Wait, no, I can do more. I'm sorry. I can factor out 4/5. Let me factor out a 4/5. So 4/5. So this will be 3 minus x, I think. And then I can put the -2/5 in the denominator, so I have 4 times 3 minus x over 5 times x to the 2/5. So this implies that um first of all, so when is this 0? When is so let's see. Um so f prime of x is 0 when, well, the numerator is 0. So that will imply that x is equal to 3. So when x is equal to 3, the derivative will be 0. So you just set the numerator equal to 0, and that's what you can solve for that. And you can see that x is going to be 3, and then f prime uh say does not exist. F prime of x does not exist when x is equal to 0. So this is where you could have a minimum or maximum at 3 or 0, but you're not guaranteed to have one there. So did I screw this up? Let's see. Actually, it looks like I might have done something wrong, which I'm confused about. They did product rule. I don't know why. Yeah, I must have done something wrong. Let me pull the book up. They did the product rule. It's kind of unnecessary. This is for part B. So the domain of f is the whole real line. Okay. Then the product rule. So you take the derivative. Well, they read it backwards. I don't like the way they did product rule. So derivative of that is -1 times the x to the 3/4, or 3/5, and then you don't take the derivative of the second function. You take the derivative of the first function. It's backwards to me. And then they distribute this through. Okay, all right. I guess I just made an arithmetic error somewhere. All right, so then when you set this equal to 0, you set the numerator equal to 0, and you get this, and then you solve for it, you get 3/2, and then it doesn't exist when x the derivative doesn't exist when x is 0, which is what I had. So I don't know where I went wrong. But anyways, all right, so now let's look at example 8. This one I shouldn't screw up because there's no denominator. So in this case, we want to find an absolute minimum and maximum. So we have this is example 8. And so we want to find absolute extrema, minimum and maximum, of the function f defined on the closed interval, 1/2 to 4, the real numbers, and it's given by taking x and sending it to x cubed minus 3x squared plus 1. So this is a continuous function on a closed interval, so it's definitely going to have an absolute minimum or maximum. And where could it have a minimum back? Where are the possible places it could have an extrema? Well, it could have it at the endpoints, or it could have it at the critical points. So what we need to do is we need to find the critical points first. So let's find those critical points. So we're going to take the derivative, f prime of x is going to be equal to 3x squared minus 6x, and then that's it. And if you set that equal to 0, so f prime of x equals 0, notice the derivative exists everywhere because it's a polynomial. But if you set it to equal to 0, you're going to see, well, let's just do it. So you get 3x squared minus 6x equals 0, and then you factor out 3x yeah, x minus 2, and then that, oh, no, wait, did I do this right? Maybe I'm gonna screw this one up too. 3x times x minus 2. So that should give you um the critical points of x is equal to 0 and x is equal to 2. Yes. Okay. So this is where local extrema could happen. We could have local extrema there. We have to, it's not guaranteed. We have to do some calculations. Now, both of these are in the interval, so both x equals 0 and 2 are in the intervals from -1/2 to 4. So we need to do some calculations. We need to compute the function at 0, 2, and then these endpoints and compare the values. So when you do f of 0, let's kind of do in order actually, increasing order. So f of -1 is going to be, I'm not going to go through the calculation, but if you do that, you get 1 over 8. And then if you do f of 0, you get 1. So far this one's the bigger one. If you do f of 2, you get -3. Okay, so far that's the smallest. And then f of 4, it's going to be 17. Okay, so now we just compare them and then pick out the largest, and that'll be the absolute max on this interval right here, from -1/2 to 4. So we can see that this is definitely the absolute max. And then this one right here is going to be the absolute minimum. So notice, so we had the endpoint was a max, but one of the interior points in the interval, one of the critical points ended up being the absolute minimum. So that's why it's important to compare the endpoints of the interval to the critical points of the function. So let me open the book up so there's this little like step-by-step directions on finding absolute minimum of a maximum. So, and this is for when a function is defined on a closed interval a to b. So how do you find those? So first of all, you do what we did, you find the critical points of the function in the open interval a to b. And then you find the values of the function at the endpoints of the interval. And then you compare those to the value of the function at the critical points. And that would be step 3. And then you just compare all these numbers and you just pick the biggest one and the smallest one. All right, so that's all we have for this video.